Writing a rate equation and working out the units of the rate constant. What I'm going to do in this video is just work through how to actually get a rate equation, then how to work out what the units are. I'm taking questions here from page 42 and the table on page 44 of your rates booklet. So first off, like we've seen before, we need to work out the orders of reaction. So here we've got A is always changing here, so we're going to have to be careful. B isn't changing here, so I'm going to look at A in experiments 1 and 2, and I can see that it's gone up by a factor of 2. And I can see that my rate here has also gone up by a factor of 2. So that suggests to me that this reaction with respect to A must be, if the rate's times by 2, if the concentration is times by 2 and the rate is times by 2, that the reaction must be, first order. So here in the first part of the question, I can say, using experiment 1 and 2, A doubles, rate doubles, so first order with respect to the concentration of A. Remember here that we're using the square brackets here to indicate concentration, and that the units of concentration are moles per decimeter to the minus, or moles per decimeter, which is moles decimeter to the -3, that indicating that minus, that it's moles over decimeters cubed. Then for the second part here, we've got to look and see, well, whilst B is doubling here in experiments 2 and 3, concentration of A is also doubling. So annoying here. What I'm going to do then is say, well, I know that A is a first order, or is first order. So here I've got times 2. Interesting pen going on there. We can see that's times 2. And here we've got that the rate is also doubling, going up by times 2. Excuse me while I sort my pen out. There we go, that looks a bit better. So that means then, once I've considered the effect of A, which I know when that increases by 2, because it's first order, as we've already worked out, then the rate is also increasing by 2. That means that B, even though it's been doubled, it can't have had any effect on the rate of reaction, because the only change in rate I can see is that would be attributed to A. So A is times by 2, the rate is also times by 2. B has been times by 2, but it hasn't done anything more to the rate than what A has. So we can then say about B, and pause here if you want to think for yourself, we can say for B, using experiments 2 and 3, A doubles, meaning the rate doubles, therefore 0 order with respect to B. There's been no change. B is doubled, but A is also doubled, but the rate has not gone up by more than times 2. So it's only been with the effect of A that there has been a change. Now the question goes on to say, write the rate equation for this reaction. Now for a rate equation, what we're saying is that rate, excuse me a moment, so the information from our orders that we've worked out means that rate, means that rate is proportional to A, the concentration of A in some way, and the concentration of B in some way. Now, to get from being proportional to an equation, what we need to add is a rate constant. And so we add little k. And so for this particular reaction, I can write the rate equation as R is equal to K, the concentration of A and the concentration of B. And can you see why I put A to the power of 1 and B to the power of 0? Have a think about that for a moment. A is to the power of 1 because we worked out, using experiment 1 and 2, that A, or with respect to A, we have a first order relationship. So I put the concentration of A to the power of 1. B, with respect to B, we said that the order was 0, and so I put it to the power of 0. Now, anything to the power of 0 is 1, so B actually doesn't show up in our rate equation. We can just, we can make it equal to 1, and so that we get that R is then equal to the rate constant and the concentration of A. Again, if you think about it, if you put anything to the power of 1, it becomes just itself. It's like timesing something by 1. It just stays the same. So our rate equation becomes K concentration of A. This question then asks us to look at what the overall order of reaction is. Here we just need to add the powers together. So our overall order here is the order of A plus the order of B, which in this case is equal to 1. Now what the exam questions always get you to do here is, once you've written your rate equation, you've worked out what the orders are with respect to your concentrations of your reactants, it then asks you to work out what K would be. So you have to rearrange this equation to get it in terms of K. To do that, I'm going to take my concentrations, in this case it will just be A, and I'm going to put it underneath the rate. So if you like, I'm going to divide both sides by A. So there's my rate equation, R equals Ka, and then I rearrange it by dividing both sides by A, so I get that K is equal to R over A. And then what I have to do, if I want to work out K, what the value of the constant would be, I go back to my table and I choose one set of experimental data. It doesn't matter which one. It can be experiment 1, experiment 2, or experiment 3. What's important is that you only use the data from one experimental set. So I can't jump around the table. If I've chosen experiment 1, I take the concentration of A in experiment 1, and I take the rate that was in experiment 1, and I put them into my equation. So the rate obviously being R, concentration A being the A in square brackets. So I come back and put them in my equation. So from experiment 1 data, I've got that K is equal to 2 over 1. And so the answer is equal to 2. Now, once you've put that data in and you've got a value for K, you're not quite finished. You then need to work out what the units of K would be. So in this case, if we look at our units, we go back up and we look what the units of rate are. The units of rate is equal to moles per decimeter cubed seconds to the minus 1. And the concentration of A, units for concentration, are moles per decimeter to the minus 3, or decimeters to the minus 3. So if we put that in our equation, then K is equal to the units of rate, moles per decimeter to the minus 3 seconds to the minus 1 divided by moles per decimeter to the minus 3. So my units for K, I've got to try and cancel out what I can. Now I've got moles both on top and underneath, so they cancel. And I've got decimeters cubed both on top and underneath, so they'll cancel out. It's like saying, what's 5 divided by 5? It's just 1, isn't it? So I can take those out, I can take those out, and I'm left, in this case, with my units of K as equal to seconds to the minus 1. So the units, seconds to the minus 1, because the other units have cancelled out. Now, if you're thinking ahead from here, my rate equation is determined by the orders of reaction. So the units of K will be different for every rate equation that you that you work out. So we need to have a look at how we work out the units for different overall orders of reaction. So here I'm going to talk through the table which is in your notes on page 24. Key things to highlight, if you haven't done so already, is that the units for the rate constant depend on the order of reaction. They're different for every reaction. And you've always got to check what the units are in the question, because it might be that they've put them into minutes rather than seconds, for example. They might have done something funny. Remember, the square brackets mean concentration, and concentration, remember, is moles per decimeter cubed. And remember that rate is measured in moles per decimeter cubed per second to the minus 1. You must remember that that is the units for rate, very important, and the units for concentration. Time obviously is normally measured in seconds, but they might throw in minutes. If they do, you just use minutes instead of seconds. So what we've got in this table is the overall order of reaction, the rate equation that would come from that, and rearranging that equation so that we can find K as the subject, and then we can work out what the units are of K. So looking at this first one with an overall reaction of 0, what we're saying is that, I'll just find my pen, what we're saying is that in the rate equation R equals K, and then our orders of, say, we're using concentrations A and B, with an overall order, what this equation is saying is that A and B both have no effect on the rate of reaction. In fact, they're both to the power of 0. They're both 0 order reactions. So therefore, they cancel out. They just become 1s in the equation. And so we're just left with R equals K. Cancelling that one, and that one out. And so you're just left with rate R is equal to K. In this case then, what will the units be? Well, R is equal to K. The rate is measured in moles per decimeter cubed per second. Since K and R are equivalent to each other, it's just the units of rate. So the units of K this time are exactly the same as the units of rate for an overall 0 order reaction. So there you have the units of K. Moles per decimeter cubed per second to the minus 1. Now in a first order reaction, as we've seen just previously on this video, rate is equal to K concentration of A. So we rearrange and we get K is equal to R over A. So this time we have to think about, as I've done before, cancelling the units. That is when there's only one concentration term in the equation, it's got an overall order of 1, then what we find is that we get moles per decimeter cubed per second, which is the units for rate, divided by the units for concentration. You can then cancel those with those, since you've got the same on the bottom and on the top, and you're left with the units second to the -1. Now, in a second order reaction, things start to get a little more interesting. Let me just flip over onto a new page. In a second order reaction, this could come from a couple of different types of rate equation. Rate in this case could be equal to K A to the 1, B to the 1, meaning that A and B are both first order, and then I add those two powers together. Or it could be that the rate is just equal to K A in a second order reaction, so that I've got just A as a second order, or A and B as first orders. In each case, you're adding the powers together, and in this one perhaps B is 0 order, so you just end up in both cases with an overall order of 2. Then in both cases you'd rearrange the equation, so R is equal, sorry, not R is equal, K is equal to R over A B. I think we'll look at this one first. So when you get that situation, again you're going to put in your units. So let's focus on this expression, and I'll go back to the table. So here we've got, for a second order, we've got the rate as A times K times A times B, both of these being first order, so give an overall order of 2. So K, when I rearrange it, is equal to R over A B, which means then I put again the units of rate on the top, so that's just the units of rate on the top, divided by the units of A times the units of B. When I've got that situation, I can again just do some cancelling. So moles per decimeter cubed there, moles per decimeter cubed there. And what I'm left with then is seconds to the -1 on top, moles underneath, decimeters cubed underneath. What I have to do to finish this off is say, well, I'm going to bring the decimeters and the moles up on to the top. And to do that, all I do is take the power, whether it's negative, if it's negative and I change it to positive, or this is moles to the power of 1, if you imagine, if I take that up to the top, I have to put that as moles to the -1. So I end up with decimeters cubed. So I've taken that decimeters, put it on top, so I've got rid of the negative sign. Moles to the -1, because it was to the power of 1, I've taken it onto the top. So I've replaced, or put a negative sign in to indicate, and I've left my seconds to the -1 the same. Notice that it's good practice and the convention to put the positive indices, so here the decimeters cubed, at the front of the units. On the mark schemes, this is the mark that they want, They would allow it if you switched the two round, but it's good practice to always put the positive indices first. Now looking at a third order reaction, again a third order reaction could come from a number of different types of reaction. For example, you could have 3 first order concentrations to make up a third order reaction. Remember, you're just adding the orders together to find out the overall order. Here we'll look at Ka squared B. So again, you rearrange the equation, you divide both sides by a squared and b, so that you get K equal to R over a squared b. You put the units of rate on the top again, and you put the units, the concentrations of A and B underneath again. Once again, I can see that I can do some cancelling, because here I've got moles to the decimeters to the minus 3, moles decimeters to minus 3. So that can cancel with that. Now I'm left with moles decimeters to minus 3 squared. Now I can take this out of the brackets, and I can just say that is the same as moles decimeter minus 3 moles decimeter to minus 3. So it's like I've got 2 of them. So if I times moles by moles, I will get moles squared. And if I times decimeters by decimeters, I get decimeters to the minus 6. So in this case, notice here I'm adding the minus 3 and the minus 3 together to get decimeters to the minus 6. So my final answer then, if I just remove that bit of working, what I'm left with is seconds to the minus 1 on top, with moles squared underneath and decimeters to the minus 6 underneath. So I take decimeters to the minus 6 up to the top, so I remove that minus sign and I get decimeters to the 6. I take my moles squared up to the top, so I have to put a minus in front of that too, so I get moles to the minus 2. And then the seconds to the minus 1 is on the top already, I leave it alone, so I get decimeters to the 6, mole to the minus 2, seconds to the minus 1. And so you have, on page 44 of your notes, the units for a 0, first, second and third order. Notice that they are all different, and in every exam question you have on rates, they will get you to work out the units of the rate constant. It's one mark which is so important. In the following videos, we will do more calculations which look more like exam questions and take you through working out orders, the rate equation, calculating what K is, and then calculating the units for K.